Hello there. In this module we consider inference on population variances, and so it's not enough just to say something about the mean of a population or means of a population or the medians, but we need to say something about the dispersion or the spread or variability of a population. And in particular we want to look at statistical inference on population variances. So here in many situations the variability of a population's values is as important as the population mean. So for example, suppose if we are dealing with product improvement, suppose we're dealing with say a drug that's on the market and it's labeled as being a 20 milligram drug, that the mean value of the amount of drug in that tablet is very close to the target value, but also that the variability is very small around that mean. Okay, so we want to know something about the variability of an underlying population as well. And so the starting point for us here is dealing with one population variance. First we're going to look at a point estimate and an interval estimate for a population variance. If you recall, when we dealt with the binomial distribution and the normal distribution, we talked about it having a population variance. In fact, even when we dealt with data sets, we talked about them having population variances. And that the point estimate for that, the natural point estimate, was the sample variance here that we have worked with in the past. That's the natural point estimate for sigma squared. Now it turns out that S squared is, let's see here, let me get back to the pen, is an unbiased estimator for sigma squared. That is, that means the average value of S squared is equal to sigma squared. And so in some sense that's a nice property for this estimator to have. Next we're going to look here at the sampling distribution of S squared. And so the reason is it's not enough just to have a point estimate for a parameter. Those are often too rigid, and so we want to develop an interval estimate as well as hypothesis test for the parameter. In order to do that, we need to know something about the sampling distribution of S squared. And we did this earlier, this sort of thing earlier, when we wanted to know, when we wanted to do inference on a population mean mu, we had to know something about the sampling distribution of y bar. So you recall that in the same way we needed to know something about the sampling distribution of y bar to perform inference on mu. We want to know something about the distribution of S squared to do inference on sigma squared. Now this theorem gives us insight into that. Okay, if you recall, previous theorems told us something about x bar being normal or approximately normal. Here we're dealing with the distribution of S squared. Okay, I said x bar earlier. Here I have written y bar. Same thing, the sample mean. Theorem: let y1, y2 up to yn be a random sample from a normal distribution with a mean of mu and variance sigma squared. Then n minus 1 times sigma squared, I'm sorry, that's not right, n minus 1 times S squared over sigma squared. That follows what's called a new distribution for us. It's called the chi-squared distribution, and it has degrees of freedom. In this case, the degrees of freedom are n minus 1. Now if you notice, excuse me, that I have not exactly the distribution of s squared that I'm dealing with, but I'm dealing with n minus 1 times s squared over sigma squared, a function of s squared and its distribution. It turns out that's going to be helpful for us. This is the theorem. We're not going to prove it, just going to make a statement of it. One important thing with this theorem is that we're assuming we have a random sample from a normal population, so we need to be mindful of that. Okay, so what is this chi-square distribution? It's a new distribution for us. It is in some ways similar to the t distribution in that it has a parameter within it called the degrees of freedom. But let's spend a moment here and look at the chi-square distribution, as it has a role for us now as well as later on in developing other statistical methods. But the probability density function of a chi-square distribution is of this form here, and so this will be the last time you see that in this class, because that is it's a very complicated mathematically. The thing that I want you to know here is that the density has a domain of non-negative values, that is x is bigger than or equal to 0, and k here is this quantity that's called the degrees of freedom. Okay, and so this thing, the degrees of freedom, is really what's going to govern the shape of the distribution for us. All right. Shorthand notation, we're going to say a variable is distributed chi-squared with k degrees of freedom. We're going to use this notation here. This letter right here, or this letter rather, is a Greek symbol chi with a square on top. Okay, so moving along, here's a graph of the chi-square distribution. This is from Wikipedia. It turns out that the mean of the chi-squared is the degrees of freedom, and the variance is 2 times the degrees of freedom. And also it turns out as k increases, the chi-square distribution approaches the normal distribution. But what I want us to note here is that the chi-square distribution is generally a right-skewed distribution, and you can see that for these varying values of degrees of freedom. When the degrees of freedom is small, here it actually doesn't have a mode. It has it goes up here and has a vertical asymptote here. When k is 2, it has a y-intercept at a half. When k is 3, now it starts to have a mode, and it's right skewed. And when k is 4, still has a mode. The right skewness starts to lessen as the degrees of freedom increases. But anyway, those are some plots of a chi-square distribution. Now, similar to the t distribution that we looked at previously, we're not too concerned with modeling using the chi-square distribution. Rather, we will be interested in finding percentiles using a table or a calculator or your computer from this chi-square distribution. Okay, so with that background, let's move to some inference here. An actual confidence interval for the population variance. Here, in our assumptions, we require that a random sample come from a normal population. Now, unlike the t-interval, this confidence interval is not robust to departures from normality with moderate to large data sets. If you recall, the t-interval which actually became the z-interval for population mean mu, we could start to relax the normality assumption if as our sample size increased. So if we had a large sample size, the normality assumption was not as important. And the central limit theorem was driving that result. But now the CLT actually does not play a role for us in the sampling distribution of that quantity there involving S squared. So we need to be mindful, very careful about applying these procedures and that we have good evidence that our population is normally distributed. Okay, the general confidence interval for sigma squared is given by this this expression here. Here's our lower bound, and here's our upper bound. Okay, and so it is n minus 1 times s squared over chi-squared u. Chi-squared u is an upper tail percentile of a chi-squared distribution, so you'll need a chi-squared table to compute that, or a calculator or computer. And chi-squared L, which is over here, it's in the denominator of the upper bound for the interval. That is the lower tail chi-squared value with an area alpha over 2 to its left. All right, so we'll actually flesh that out in an example in a little bit, but let me clear these here. The above interval formula is a result of the sampling distribution. In other words, where did this come from? Did we just pull this out of a hat? Where did this come from? So we're going to develop it here. It's a consequence of the sampling distribution of this ratio here. Recall we had a theorem that said this ratio is chi-squared with n minus 1 degrees of freedom. Okay, so I want you, with that in mind, I want you to consider the following picture. Where here I've got the chi-squared distribution. Now what's different about the chi-squared as compared to the t or the normal is that it starts at 0 and goes on to positive infinity. Now I'm going to pick off two chi-squared values. I'm going to pick off an upper value, chi-squared, I'll say u, and the area under the curve to the right of that value is alpha over 2. And I'm going to also pick off a chi-squared L, okay, such that the area under the curve to the left of that value is alpha over 2. And so what that means is that the area under the curve between the two is 1 minus alpha, right? Because the total area under the distribution must be 1. Okay, so with that picture in mind, we would say that would inform us that, hey, the probability that any chi-squared variable being between chi-squared L and chi-squared U, that probability is 1 minus alpha. The area under the curve between these two values is 1 minus alpha. So anything that follows a chi-squared distribution I can plug in here, and that probability statement would still be true. So I'm going to move along up here. What follows a chi-squared distribution? Well, this follows a chi-squared distribution. So I'm going to replace that for this middle term in the probability statement. So I'll have n minus 1 times s squared over sigma squared there in the middle. And that's between, this is chi-squared L, that's chi-squared U. Again, that probability is 1 minus alpha. So what I'm doing here ultimately is I am deriving the interval formula for sigma squared. And in order to do that, I want to isolate sigma squared. I want to get sigma squared in the middle of these two inequalities here. And a first step in doing that would be to maybe get sigma, or to move n minus 1 times s squared out of that middle term. And so the way I would do that is I would divide everything in this probability statement by n minus 1 times s squared. So I'm going to have chi squared L over n minus 1 times s squared, and that's going to be less than 1 over sigma squared, and that's going to be less than chi squared u over n minus 1 times s squared. So just using a little algebra to try to isolate sigma squared. Now I don't quite have sigma squared in the middle, but I have 1 over sigma squared in the middle. And so what I can do though is if I flip this, if I flip that, take the reciprocal of it and have sigma squared, that would be okay. But the thing about taking the reciprocal is that changes the direction of the sign. And so let me kind of remind you here. So we know that 2 is less than 3, right? But is 1/2 less than 1/3? No, it's not. I took the reciprocal of both sides of that inequality. That's not true. Rather, 1/2 is greater than 1/3. And so the sign has to switch when you take the reciprocal of both sides of an inequality. Okay, so this sign is going to become greater than, and I'm going to take the reciprocal of this. That means I'm just going to have n minus 1 times s squared on top times s squared u in the denominator there. And then over here I'm going to have, this sign is going to flip, and I'm going to have n minus 1 times s squared over chi squared L. And all the probability of that is 1 minus alpha. Okay, so almost there. Now you could stop here, but typically when we think of inequalities and we're reading them from left to right, we like them to be in the less than direction. And so I'm going to rewrite the inequalities under this probability statement as the probability that n minus 1 s squared over chi squared u, notice chi squared u, this quantity is going to be less than sigma squared, and sigma squared is going to be less than this quantity here, n minus 1 times s squared over chi squared L, and that's going to equal 1 minus alpha. Okay, so what we have here overall, this is the lower bound and this is the upper bound of my confidence interval. And that's the derivation of it, and it ultimately started from, hey, knowing the distribution of n minus 1 times s squared over sigma squared. Okay, I do want to make a statement here. I believe I skipped it earlier in the video, is that a confidence interval for sigma is found by taking square roots throughout the interval. So if I want a confidence interval for the standard deviation of the population, I'm going to take the square root of this quantity here and of this quantity here. Okay, so let's see here. Alright, moving along to an example. So this is an important example here for someone that might be interested in manufacturing industry. Bolts are an important part of things that hold stuff together for us. What I'll do, instead of me talking through this example, hit the pause button, you read through it, and then we'll come to work it out. Okay, so hopefully you've got a good understanding of this problem. When you think about bolts, they better fit into wherever they're headed, the nut they're headed into, or some respective application. If they're a little bit too big or a little bit too small, they're not going to work. And so the thing that measures the variability in the bolt diameters for us is going to be the standard deviation. And we want to construct a 95% confidence interval for the standard deviation of all bolt diameters, of all quote-unquote 10 millimeter bolt diameters produced by this manufacturer. And so here we're going to use this formula. I'm going to take, let's see, I'm going to take this formula, but I'm going to take the square root throughout because I want a confidence interval on sigma, not sigma squared. So I'm going to use here the square root of n minus 1 times s squared over chi squared u. That's the upper chi squared value. And the upper bound is going to be square root of n minus 1 times s squared over chi squared L. Okay, so I've got that set up there. I can just plug in the values I need now. Alright, so I have the square root of n minus 1. Well, what's n? Here, n is 12. Okay, and also the standard deviation is 0.047. You can verify that if you want to take this data set, put it in JUMP or your calculator to compute that standard deviation. So I plug in here. I'm going to have 12 minus 1 times s, in this case s squared, 0.047 squared divided by chi squared u. What is chi squared u? Let me look over here on the chi squared distribution. So here I'm dealing, I don't like that picture. I've got a right skewed chi squared distribution here, and chi squared u is going to be an upper chi squared percentile. Okay, now just to be clear, the degrees of freedom you recall is n minus 1, so my degrees of freedom here is 12 minus 1 or 11, and I want a 95% confidence interval. So I'm going to split the alpha in two. This alpha here is going to be I'm going to split the alpha in two for the right tail area. I'm going to have 0.025 there, and later I'm going to look at chi squared L and have, that's where the area here is 0.025. But chi squared u here, what we need to do is go to our chi squared table, look that up. I've got the book here. Here's a chi squared distribution, table 7 of your book. I'm going to be looking for what does this give me? This gives me the right tail probability here, and I need for the chi squared u, I need the right tail probability to be 0.025. Okay, so here we are. I'm going to be in this column, 0.025. And the degrees of freedom again is 11. So my chi squared u is 29.92. Okay, 29.92. So let's go back to our notes here. This is 29.92. Chi squared L. Chi squared L is that lower value. So I'm going to go back to the chi squared table here. That's going to have, again, if you look here, this is giving right tail areas. So if my left tail area is going to be 0.025, my right tail area has got to be 0.975. So I want to look here of the chi squared value in that column. Degrees of freedom again is 11, and that chi squared value is 3.816. Okay, so going back to our notes, this value is 3.816. All right, so here I'm going to have 21.92 comma, upper bound is going to be, again, 12 minus 1 times 0.047 squared divided by the chi-squared L, the lower percentile, is 3.816. Alright, you can work through the math if you want to. You'll need to make sure you verify this in your calculator, but the lower bound is 0.0333, the upper bound is 0.0798, and so what we would say is we are 95%, as an interpretive statement here, we are 95% confident that the bolt diameter standard deviation for all bolts, or for all, let me back up, all quote-unquote 10 millimeter bolts produced by this machine is between 0.0333 and 0.0798 millimeters. Okay, that's our interpretive statement of that. If you want to think about how could that be applicable, if you think in terms of an empirical rule idea, remember the empirical rule suggests that about 95% of the distribution is within 2 standard deviations of the mean. So if you took the mean of this population, add and subtracted 2 times the standard deviations, that would give you a sense of where most of the bolt diameters would be. I do want to say here something that's important is, again, this method, this interval method here, has the assumption of a normal population, and so really we should check that for this data set. Okay, so the question here is the population normal? Well, we don't have the whole population in front of us. Is the population normal? Well, we don't have the whole population in front of us, but we do have a sample of size 12. We can check a QQ plot, check the QQ plot for the 12 data points, and if it looks close to linear, then normality assumption is tenable, defendable, and we'll go with it. If it's not linear, then we need to revisit this problem really with a different kind of technique. Actually, it would be a non-parametric technique. We're not going to cover that in this class, but they are out there. But for us, this is typical enough, or it's common enough to have data that comes from a near normal or normal population for us to apply this sort of confidence interval. Next, we move on to a hypothesis test situation for a single population variance.